Okay, so this is the video lesson on discussion 1-2 for both Chem 1 and IB Chem 1 on nuclear radiation. And so we're going to talk about mostly balancing nuclear equations and also solving half-life problems. So in class, we talked a little bit about some of these statements about radiation that are true or false. We are exposed to radiation all the time. Nuclear materials and their toxicity, it really depends on the half-life. So some nuclear materials remain highly toxic for a very long time, others decay really quickly, so we'll talk about that. So this is kind of an opinion question about which one you'd rather live closest to, so we'll talk about some of the pros and cons of nuclear energy later on in the discussion. And it is true that most people are exposed to more radiation from radon in their homes than they are from nuclear power plants, on average of course, but nuclear power plants aren't necessarily the main source of radiation exposure for most people. So what is a radioisotope? These are just atoms of an element that emit radiation. So they have unstable nuclei, and the reason they have unstable nuclei is because there are too many neutrons compared to the protons. There's a high neutron to proton ratio. Now, in order to become more stable, these unstable isotopes simply decay. The nuclei emit particles, and that makes the nucleus more stable. Interestingly, it also usually changes the identity of the element because it changes the number of protons. Now, there are three major types of decay that we're going to talk about in this class: alpha, beta, and gamma. Now, in terms of their charges, if we were to take a radioactive sample that emitted all three types of particle and put them through an electric field with charged plates, we would find that the beta particles would be attracted to the positive plate because they have a negative charge. Alpha particles have a positive charge and would be attracted to the negative plate, and since gamma rays are neutral, they would not be attracted to either of the charged plates. Now, one really important thing to understand about these particles is how easy they are to shield or to block. And so this says something about their penetrating power, how much they can get through barriers that we might put in their way. So alpha particles are very easy to block. They have very low penetrating power. They can be blocked by paper. Your skin also blocks alpha particles. Beta particles, on the other hand, it requires a little bit more to block these. So aluminum, some kind of metal that's, around a centimeter or a little less thick will usually block beta particles. And gamma rays are very hard to block. So typically, to effectively block them, we need thick lead or ideally thick concrete. So let's talk about what an alpha ray is made of. It's made of alpha particles, and each alpha particle has 2 protons and 2 neutrons, which means since it only has 2 protons, which are positively charged, and neutrons, which are neutral, that means that it has a positive 2 charge. It's basically like a helium-4 nucleus, not the whole atom because there's no electrons here, but just the nucleus, 2 protons and 2 neutrons. And again, we can stop this by a sheet of paper. Beta rays are made of beta particles, and they have a charge of -1 and a mass of 0, like an electron. Now you might be wondering, how do we get an electron from the nucleus? And that's a good question. So these originate when basically a neutron splits into a proton and an electron. So it emits a beta particle, which is basically an electron, and converts a neutron into a proton. And again, 6 millimeters-ish of aluminum stops most beta particles. Now, gamma rays are just high energy radiation that possess no mass and no charge. Okay? They usually accompany alpha and beta decay, and they account for most of the lost energy during the process. You need pretty decently thick lead or ideally concrete to stop gamma rays, but it's pretty hard to stop 100% of gamma particles. Okay, so to summarize, alpha particles are basically helium nuclei with a mass of 4 and a charge of 2. They can be stopped by paper, and this is how we would represent them in a chemical equation. Beta particles are electrons with no appreciable mass. Of course, they have mass, but it's so small that we say it's negligible. A charge of -1, and that's how we write them in nuclear equations. And finally, gamma particles are basically just high-energy photons with no mass and no charge. And when we write their symbol, we use the Greek letter for gamma. So pause this for a minute and get anything you need to down. Remember, there's guided notes for you on Classroom. And then press play when you're ready. Okay, so let's talk about nuclear equations. So when an atom undergoes nuclear decay, the nucleus breaks into two pieces. So we have the original original parent nucleus, and then that breaks to create the radiation particle, alpha, beta, or gamma, and the new daughter nucleus, as we call it. Why do we call it that? I don't know. Okay, now let's look at this equation closely. Look at the mass numbers on both sides of the equation. If you look carefully, you'll notice that the sun is the same on both sides of the arrow. So think of the arrow as like an equal sign, right? 232 equals 228 plus 4. The atomic numbers are the same. 90 on the left side of the arrow equals 88 plus 2 on the right side of the arrow. Okay? This makes sense based on the law of conservation of mass, right? We can't just have mass disappearing. The total has to be the same on both sides. Now, when we look at alpha versus beta decay, we see something kind of interesting. So the first is an example of alpha decay, which we just saw. The second is beta decay. Now, because the beta particle has no appreciable mass, its mass is negligible, we see that the mass number of the daughter nucleus doesn't change. But since it has a -1 atomic number, the atomic number of the daughter nucleus actually goes up by 1. Okay? If you look, again, think of the arrow as an equals sign. 90 equals 91 plus -1. This will trip a lot of people up if you're not being very careful. Okay? Now think about why this makes sense, right? When the beta particle was emitted, a neutron turned into a proton. So we have the same total number of protons and neutrons, but now one of those neutrons has become a proton. Okay, so let's look at these statements. In class, we dragged dots on Pear Deck to this, but which involves a larger loss of mass? Well, that would be alpha, right? Because beta particles have negligible mass. So when they're lost, there's no change in the mass number. Creates a daughter atom with a greater atomic number. Well, that's a beta particle because it converts a neutron into a proton. Loses an electron from the nucleus. That's basically the definition of a beta particle. Loses 2 protons and 2 neutrons from the nucleus. That's the definition of an alpha particle. And the particle produced has a positive charge. Alpha is the one with a positive charge because it consists of 2 protons and 2 neutrons. Okay, so gamma decay, we haven't talked about that in nuclear equations yet, and part of the reason is that if you look at a nuclear equation, you wouldn't necessarily know that gamma radiation is being given off because it has no mass and no charge. However, just because we're not going to talk about it in these nuclear equations doesn't mean that it's not important. It's very important because it's the most dangerous of these 3 types of radiation, right? It has the strongest penetrating power, so it's still important to be aware of gamma radiation and what it is, even though we're going to talk about it a little less as we apply some of these concepts. Okay, so let's talk about balancing these nuclear equations. Now, when I'm trying to find the missing particle here, I'm actually going to go to my document camera. So I have 218 is the mass number of this isotope of polonium, and it decays by alpha decay. So when I'm trying to find the missing number, remember that we're treating this arrow as if it's an equal sign, right? So 218 has to equal 4 plus something else here. So what is that number? That number is 214, because 4 plus 214 equals 218. Okay, so to find the atomic number, 84 equals 2 plus what? 82. Now, how do we figure out which element this is? Well, we have to use our periodic table and the atomic number, because this is what identifies an element. So element 82 is lead. Now, you might notice that this mass is not going to match the mass on the periodic table, because remember that the periodic table is a weighted average of all of the isotopes. So you shouldn't expect them to match because this is talking about one specific isotope. Okay, let's go back to our slide. All right, so this gives us the alpha decay of polonium-218. Okay, now I want you to pause for a second and try this. You're going to try to find the original parent nucleus here, and press play when you think you have the answer. Okay, so in this case, again, we need to make sure that the sum of the mass numbers on either side of the arrow are equal, and the same for the atomic numbers. So 222 plus 4 equals 226, and 86 plus 2 equals 88. And looking at the periodic table, element 88 is radium. Okay, so now I want you to pause and see if you can use the mass and the atomic numbers to figure out what type of radiation is emitted, alpha, beta, or gamma. And again, look very closely at the change in the atomic numbers to figure this out, and press play when you're ready. Okay, now, the mass number isn't changing from the parent to the daughter nucleus, so the mass number of our particle has to be 0. But the atomic number is going up by 1, so to balance that out, the atomic number of our particle has to be -1, and that is a beta particle. All right, so let's talk about how long radioactive things are radioactive. So in class I posed this question, and it's kind of a trick question because the answer is technically forever. If I have 1,000,000 atoms, even if the half-life's relatively short, most of them will have decayed, but not necessarily 100%. So the radiation dramatically decreases over time, but typically we still have at least a few atoms that still have yet to decay. Now, true or false, people can be radioactive. Well, sure, nuclear medicine is really, really common, and so while people don't remain radioactive, some of you may have actually had some kind of nuclear medicine treatment or know somebody who has. And if you were to have a nuclear medicine treatment and then check to see if you were radioactive with a Geiger counter, you absolutely would be. So nuclear medicine is actually a really important part of our lives, and we'll talk about some of the things that it's used for. Okay? Now, when does a sample of radioisotope stop decaying? Never really. It approaches 0, but never really gets there. So the half-life is the amount of time it takes on average for half of a radioisotope to decay. If I'm being really precise, it's the amount of time in which a given nucleus has a 50-50 chance of decay. So, to put this a little more clearly, if I had 100 grams of a substance, in one half-life, 50 of those grams would have decayed into the daughter nucleus. Okay? And so it's never really going to stop, because if I'm only dividing by 2 every time, I'm never going to get to 0, technically. So, the half-life of strontium-90 is 29 years. If I had 10 grams of strontium-90 today, 29 years from now, I'd have 5 grams left. After 58 years, that would be a second half-life. I would be down to 2.5 grams. All right, so I want to make sure that you know that radioisotopes are really important and really common. So in class, I had everybody go research and come up with a commonly used radioisotope. So people found radioisotopes that are used for all kinds of different medical applications, like technetium-99 and iodine-131. They found that americium is used in smoke detectors. There's lots and lots of different radioisotopes. So I'd encourage you to make sure you could give at least a few examples of things that are important. Uranium-238 is used in nuclear reactors. There's just so many that are important to our lives. So the last thing that we're going to do is calculate half-life. And whenever we do a half-life problem, we're going to use 4 things: the starting amount, the final amount, the half-life, and the total time. And in any given problem, you'll be able to find 3 of these, and you'll be solving for the 4th. So let's look at an example. Iron 59 is used in medicine to diagnose blood circulation disorders, and we know the half-life is 44.5 days. How much of a 2-gram sample will remain after 133.5 days? Okay, so I'm going to go to my document camera once I get this data down, and I'm going to show you how I would solve this problem. All right, so here we have the initial amount, which is 2 grams. We have the half-life, which is 44.5 days, and we have the total time, which is 133.5 days. So let's take a look. Now, I know that every time a half-life goes by, this will divide in half, but I need to know how many half-lives will go by. So to figure out the number of half-lives, I can take the total time divided by the half-life. And in this particular case, there will be 3 half-lives. I'm going to use arrows to represent half-lives. So that means in the arrow diagram that I'm about to draw, I'm going to have 3 arrows. All right, so after my first half-life, I'm going to have 1 gram. After my second half-life, I'll have 0.5 grams. And after my third, I'll have 0.25 grams. So this would be my final amount. And notice I write these every single time, and I encourage you to do the same, but feel free to abbreviate them because starting amount, final amount, half-life, and total time do take a while to write. Okay? I think it's really important to show the arrows every time. Otherwise, I've noticed that people have a tendency to do 1 too few half-lives. They divide by 2 not quite enough times. Okay, so just be very careful with that. All right. So let's take a look at another example. This example says the half-life of isotope X is 2 years. How many years would it take for a 4 milligram sample of X to decay and have only 0.5 milligrams remain? Okay, so this is a little bit different because we're solving for something different here. In this problem, we want to find the total time. So what we really need to know is how many half-lives did it take to get from 4 to 0.5? So I'm just going to start drawing arrows. After 1 half-life, how much did I have? I had 2 because it divides in half. After 2 half-lives, I have 1. After a third half-life, I have 0.5 milligrams. So it took 3 half-lives to get from my starting amount to my final amount. So you might be tempted to say 3, but that's not what it actually asked. It asked how long that took. Remember, each half-life is 2 years. So that means that this took a total of 6 years. And that is my final answer. Okay, I want you to try this one on your own, and then we'll go over it. Here, you're actually working backwards to the starting amount, which is sort of a different kind of an approach. All right, so you have the final amount, the half-life, and the total time, and you have to work backwards. All right, so pause, and then when you're ready, press play. All right, so let's take a look at this. Now, each half-life was 1 minute, and the total time was 4 minutes, which means that we have 4 half-lives. So that means we're going to need 4 arrows. Now, we're starting with the final amount and working backwards. So going back in time 1 half-life, I would have had 3 milligrams. Going back in time 2 half-lives, I would have had 6 milligrams. Going back in time 3 half-lives, I would have 12. And my 4th and final half-life would bring me to 24 milligrams. So that's my final answer. All right, and then one more example. And here we're going to be solving for the half-life. So we haven't actually done that just yet. All right, so pause and try this problem, and then I will show you on the document camera. We have the starting amount, the final amount, and the total time, and we are solving for half-life. Okay, so I have starting amount, final amount, and total time. I need to find the half-life. So again, I need to know how many half-lives it took to get from 20 to 2.5. So again, I recommend drawing these arrows every time. It really doesn't take very long, and it prevents you from making avoidable mistakes. Okay, so after 1 half-life, I had 10. After 2, I had 5. And after 3, I had 2.5 grams. So it took 3 half-lives to get from the starting amount to the final amount. So 3 total half-lives took 90 years. I know this whole time was 90 years. Each one must have been 30 years. So that means that the half-life is 30 years. Now, We can also find half-life from a graph. So in order to do that, I have to look at my starting amount on the graph and find half of it. So here it's percentage, so I'm starting with 100%. So I'd look down to 50%, because that's when half of it is gone. I'd draw a horizontal line to the curve, and then look down. And you would see it's 25 days-ish, somewhere between 20 and 30. And so this allows you to also figure out how long it took to get to 40%, or something that's not on an even half-life. But to find half-life from a graph, you look at half of the starting amount and see how long it took based on the curve to get there. All right, so the last thing is fission versus fusion. So I just want you to be aware of the differences between fission and fusion, because you'll see them, they occur in very different places. So fission is when one larger nucleus splits into two. And so you see this is what happens in nuclear reactors. Okay? Fusion is when two nuclei fuse together, hence the name, right? And so fusion occurs actually on the sun. Both of these release a lot of energy. Fusion releases just a tremendous amount of energy. But it takes a lot of energy to initiate the reaction, a tremendous amount, and it produces just a tremendous amount of energy. So both difficult to initiate and difficult to kind of contain. So it's important that you're aware of some pros and cons of using nuclear energy, just because it is something that I think comes up in everyday life, and so I think it's important for you to understand. So from thinking about pros of nuclear energy, it's pretty efficient, especially compared to coal. Gram for gram, it's many, many, many times more efficient. I think I read somewhere that uranium is something like 500,000 or 5 million. It's a lot more efficient than coal, okay? It requires less material to produce a lot more energy. Now, as far as other environmental pros, it's much cleaner in terms of air and water. You might have seen gases being emitted from nuclear reactors. That's steam, okay? Whereas coal obviously releases particles that are major air pollutants. There is, as a con, the fact that we do have to store the nuclear waste, the spent fuel rods, and that can be challenging. The biggest con that people always think about is the risk of a meltdown, but realistically that's exceedingly rare. And people think of Chernobyl, but based on Chernobyl, a lot of the protocols as far as safety have been changed. In terms of economics, it's very costly to build a nuclear plant in the first place, but relatively inexpensive compared to certain other sources to maintain and run the plant once it's been constructed. It's just things to think about. There's not a right or a wrong answer as to whether we should be using more or less nuclear energy, but I think it's important for you to be informed so that if this issue comes up and you need to be able to make an informed decision about what you think, you can do that. All right, so let me know if you have any questions, and I'm also making quick videos to go over half-life and nuclear fissions.